our third day. We are still continuing until Thursday, 5th of February, from 9:30 a.m. until 5:30 p.m. With lunch break between 1 and 2 p.m. Of course, as we know, it depends of trainers if they want to give some break, like a coffee break in the middle of their sessions. But of course, your participants, if you feel that we should have some break, 5 minutes, 10 minutes, feel free to let us know. Today, for our morning session, we have a speaker, Francesco Fiusco from NCC Sweden, and he will be talking about PyTorch Lightning. And in the afternoon, we are having trainers from NCC Belgium, Geert Jan Bex, and from NCC Italy, Riccardo Scheda. So, yeah. Thank you again, everyone, for being here, and hope you will enjoy today's training. And as we tested with Francesco, technical part is working perfectly, so floor is yours. Thank you.
Thank you. Let me share my screen again. Okay, good. Hope you can see.
Yes.
Yeah, I'll try to keep an eye on Discord, but if I don't see something in good enough time, feel free to stop me and just speak up. But I'll try to keep an eye on it on my other screen. And also, as a heads up, probably today will be a bit shorter than I think we might be able to finish around 12, but we will see how it goes. So today's topic is PyTorch Lightning. I hope you saw the announcement on Discord about where the teaching material is in the usual repository. I will just copy paste the link again just for everyone to be on top of this. Yes, so PyTorch Lightning. What is it? What do we use for? And well, the second question is kind of a spoiler. So how do I use it together with, how do I write a PyTorch model together with it? And how can I use it to parallelize over several devices that may or may not be sitting on different nodes? So PyTorch Lightning is a kind of an extension of PyTorch, and it does not add functionality in the literal sense. You could see it more as syntactic sugar. If you have seen, for example, and if you haven't, you will see this afternoon, packages by the HuggingFace hub, for example, like the transformers library. They behave kind of like in a similar way, except that PyTorch Lightning potentially fits with all types of neural network, not necessarily with transformers. But what it gives you is, well, it forces you to structure the code, which is good. And that helps a lot with automation and reproducibility. At the same time, you can still access the underlying PyTorch features. So it's a good way to, get rid of a lot of the glue code that you will need. For example, yesterday we've seen some examples regarding distributed data parallel. With PyTorch, with Lightning, this becomes a lot more transparent because you don't explicitly need to change a lot to be able to take advantage of different parallelization strategies. And yeah, it makes it so that if you use Lightning types, and we will see which ones they are, then it will basically require you no changes from the code perspective to use different parallelization strategies. And these are, for example, DDP, as I mentioned already, DeepSpeed, that you will hear all about this afternoon, and FSDP, that is a way to have both model and data parallelism at the same time. And this kind of, some parts of it are kind of similar to DeepSpeed, but we will get to that later. So what do we need to do to use Lightning is to basically wrap our PyTorch model into Lightning types. And as I mentioned, this benefits development because it makes code a lot more readable, because we have to learn to split, the architecture of the model from the engineering part. So how we launch it, how long does it run, what kind of things we want to log, for example. And it also separates the data from it. So we have a lot more modular code base, which is better in the long run. So the three core ideas are that we organize code very cleanly. So we have the pure research part, if you want to call it that. So read the architecture of the model, what it's supposed to do, how the forward and the backwards pass work, where we load the data, and engineering. So really running it, both for training and for inference. And under that, of course, we have logging and checkpointing and distributed execution if we want. A lot of the stuff that we will normally need to handle explicitly in PyTorch can be handled a bit more transparently by Lightning. For example, if you want to use mixed precision, what kind of logic we want to use for multi-device runs, gradient clipping, and what kind of device and type configuration we want to use. And because of all of this, we have pretty much the same script that can run on a CPU or a single GPU or multiple GPUs using any of the supported parallelization strategies. I keep mentioning here GDP, FSDP, and Zero. Lightning has actually experimental-ish support for tensor parallelism. I know that is something that it was asked yesterday. Unfortunately, I didn't have time to prepare an example with that, but I did pull out the documentation that also Gyula posted yesterday. So yeah, unfortunately, I don't have any examples regarding that, but I can link it again and we can look a bit at what it does. So yes, the idea is that we use Lightning as kind of syntactic sugar on top of PyTorch because it lets us skip a lot of glue code, a lot of boilerplate that we will need to do, that we will need to write if we need to start a distributed data parallel process or an FSTP, or if you want to use DeepSpeed by Microsoft. I will say that that's among the main use cases. So the core API of Lightning is based on two objects, a Lightning module and a trainer. A Lightning module is actually a class that is derived from a Torch module. So it has all the methods and private and public members of a Torch module. It just adds some stuff on top so that we don't have to do it ourselves. So in the Lightning module, we describe the architecture of the network, for example, how the forward pass goes, the validation and test loops, the optimizer, what kind of optimizer we want to use, if we want to have any learning rate schedulers. It's really about how the network works. Instead, the trainer is the one that handles the engineering side of things. So it's the one that runs the training itself, that hooks into the validation and test data loaders. It calls callbacks at the runtime. Callbacks are ways that we have to inject custom code to be executed at appropriate times. One very common use case is, for example, if you want to have some kind of fancy progress bar, or if you want to do some checkpointing, then we can tell the network, at the end of every epoch, call a certain callback. And Lightning provides a few of those, sort of battery included. For example, gradient accumulation and sorts of progress bars and checkpointing. We will implement our own in an example, just for you to see what it looks like. But you will find that a lot of this comes with batteries included. So yes, this was kind of like a wall of text. So I think the best way to look at this is to start working on it. And so I set up a demo where we train a multi-layer perceptron, so basically a fully linear neural network that we use to classify flowers belonging to the iris dataset. If you're not familiar with it, I just pulled up the Wikipedia page where it's explained what it is. But basically, it's a set of 150-ish measurements of 3 species of iris. It is Setosa, virginica, and versicolor. And for each one of those, there were 4 features that were measured, that are the length and width of the sepals and the petals. So this whole script, you can download it following the links in the documentation. For those of you that are on Leonardo, I put both the code that we'll be using and the data under my public folder. So you find out this link that will also pass again in the Discord channel. And you should all have permissions to copy it. And since we don't have internet connection on the compute nodes, that also contains the data. So for those of you who are not running on Leonardo, the code assumes that the dataset itself is inside a data folder. So there is also a script to download it in the code folder, so you can do it beforehand. And the code contains this iris example.py. Let me just maybe log in on Leonardo. Or I can actually go to my work folder where I have it already. Yeah, so you will find it, you will look like this. And in the demo part of the material, I'm just dissecting it. So you can follow either from the script itself or from the material here. So I just divided into chunks and examining them separately. So the first part is our usual imports. The only new thing is importing Lightning as L. Well, this actually is PyTorch Lightning. And then what we do is basically create a model as a subclass or as a inherited class from a Lightning module. And there are 4 building blocks that have to be present here. You need to have an initializer and call the initializer of the superclass. And here you actually create the network, which we can do manually as we've done here. So here we have a hidden layer with 60 neurons, and the input is 4 features because we have 2 measurements per sepal and 2 measurements per petal. And then the output is 3 classes because we have 3 species that we are considering. So yeah, we just do like this. We will see in an exercise that we will do later that you can also use some kind of pre-made architecture. For example, if you want to do some image classification, you can use a RESTnet and use that as a backbone. So you don't have to do it from scratch. As long as you get a neural network coming out of this, it's fine. Then we define the forward pass. So in this case, we have just a ReLU after the first layer, and then we return the scores of from the last layer. And then what a full step for training does. So in this case, given a batch, we unpack the batch and a lot of times is a tuple of features and labels. Then we do the forward pass. We compute the loss. In this case, it's just cross entropy loss. I'm adding some logging here, or making sure that something that I would like to be saved is saved, which in this case is the loss on the training, and return it. And then which optimizer I'm going to use. And in this case, I'm using Adam, that is kind of like a stochastic gradient descent, just fancier. And yeah, so this is what the module looks like. Here we just describe what the network looks like, how we evaluate it, and what needs to be done during the training step, and how the backpropagation works. So this is pure description of the machine learning part of things, or deep learning in this case. Yeah, this part just summarizes what I just said. So how do we launch this? What we do is, in this case, load the dataset. So I pre-dumped it on a NumPy array because I pulled it from scikit-learn. Yeah, it creates the vector of the features, like the training data and the labels. And then I just turn it into a tensor dataset so that PyTorch can look at it. And I create a data loader. Then what happens is that I instantiate my object, this iris classifier that I've just created. And let's skip this for a second. I create a trainer object, which, as I told you before, is the one that actually handles the training. And I just tell it that I want to use a GPU as accelerator. In this case, I'm not specifying anything, so it will be one GPU for 10 epochs. And then I call the fit method of the trainer class that's just given the model and the data trains the neural network. This was very quick, so I'm not even having a validation dataset at the moment, because this is really the most bare bone thing that you can do. And we will see in the next example how to make it even more usable. One thing that I added here is this logger callback. That is this training logger object that I have not defined yet. What this does is basically calls a method that I define in the training logger callback that I'm defining below, and I just make sure that the trainer knows that he has to do this. So what does this do? The training logger is derived from the Lightning callback class, and this one comes with a set of hooks. So in this case, for example, I'm telling it to run something at the end of a training epoch. And what I'm doing is just fetching the training loss and printing it on screen. There are all sorts of hooks. For example, when a batch is being called into memory, when at the end of every step, at the beginning of every step, at the beginning and end of training, validation, or test runs, and so on. This is all written in the documentation. But basically, what we can use this for is overloading these event triggers that, as I said, it can be the start of the fitting process, the end of the fitting process, when the checkpoint is loaded, when the test epoch starts, and so on. And just inject whatever code we want. And as I said, this is very useful for logging and to save checkpoints. It can be used to do some kind of gradient accumulation. It can be used to look at the learning rate and correct it if it's needed. So if I look at the whole code, it looks something like this. I create this logger callback and the classifier as I have showed it to you. And here I load the dataset and I just fit the model. So you can try to run this yourselves if you copy it from my public folder. I corrected, if I look at the allocation script, this I tested yesterday, it's using another allocation, but yours should be correct. But what I do is just load the Chinica AI module. Lightning comes within Chinica AI, so we don't need anything else. I just do something for the data load, so the OpenMP number of threads. This is not really vital. And I just run it. And this will save some logs in the out folder. Sorry. So we can try to run it now. And look at the output. Some error to not seeing. No, it's going perfect. This should be a lot faster. Oh, yeah. Perfect. So yes, it was very fast. It just took a while to print. Yes, and you can see that, okay, I'm having my progress bar with each epoch, and my callback is being called at the end of each epoch. So just to make it very recognizable, I called it a spy report, so I couldn't be mistaken for other output. And I get the training loss. And it's decreasing, so all good, more or less. So this is the most bare bone thing that you can do. Sorry. But it's still not perfect. Why? Because in our launching script, that in this case it's in the same file, but you might want to have it as a separate training script. We're just loading the data and creating a data loader at the moment. This is not very modular because we're mixing where the training is launched together with the data loading part. And this does not make for good reusability because I may want to do some custom loading, for example, in the dataset. May want to change, for example, number of workers that are called. This does not make it very usable. So what Lightning provides us is a Lightning data module that is kind of the correspondent of a Lightning module, not for the network, but for the dataset. So the way this works is pretty similar to how the Lightning module works. So we inherit from Lightning data module, and we have a number of methods that we have to overload. So the first one is data preparation. So this runs once, and it runs only one process, even if, as we will see later, we use multiple GPUs. So this is the perfect place that you have to, for example, download the data. Download the data if you need to download, or check that the files that you want to load exists. It's really the preliminary step. Then the setup is the one that instead runs on each rank, so on each process, if you aim to use multiple GPUs. And the stage parameter can be used to prepare data for different steps of the training life cycle. So for example, this stage could be the fitting part, the validation, the prediction, or the testing. Quite often, we just don't pass this parameter because when we use this for training, then with just that particular stage, we don't distinguish between logic. But that's something that you may want to do if it's needed. And then the train data loader, validation, and test respectively return PyTorch data loaders for the different splits. So if we want to use this in our Iris dataset, what happens is that, well, I have an initializer. Here I'm just using it to save hyperparameters. Honestly, it's not something that you're forced to do. Then in the data preparation part, I basically check if the data file exists. So in this case, I have this iris.mpz in the data folder. And I just complain if this does not exist. And then in the setup part, that is the one that runs on all the ranks, this is where I do what I was basically doing before. So I load the data file, I take out the features and the labels, and then I do it actually in a more meaningful way. So I have training and validation data split, and I use the train test split function from scikit-learn. And then, as before, I convert it into PyTorch tensors, and I save it as a tensor dataset. And then when I want to run the train data loader and the validation data loader, I just return a PyTorch data loader that wraps around the datasets that I have just created. So when we want to train the network, we instantiate our data module and the callback. And then when we run trainer fit, we just pass the data module that we have. So this makes it a lot nicer because we have the data module that handles all the data part, the Lightning module that handles the network itself, and the trainer that just is used to launch everything. And I have another example here that is Iris with data module, where I do basically this. So I add what I had before plus the data module. And you can test this ourselves if you want. I'm not going to run it since it's more or less the same thing. I think there is a question here in Zoom. How do we decide what must be done in prepare data, what must be done in setup? I would say that the main discrimination factor here is if you think about this, when you think of running this on multiple GPUs, the prepare data runs only on one process. So, and it kind of happens before the main thing. So I would say I will mainly use it for checking if files exist and to download them if it's needed. So it's really preparatory work. What actually loads datasets in memory or that actually creates tensor datasets or PyTorch datasets, that has to go into the setup because we may want to do this separately on each rank. For example, let's say that we want to do distributed data parallel, then we have to make sure that each PyTorch rank loads the appropriate chunk of data that it needs to use. So that is something that instead I will do in the setup part. I hope that this answers your question. And yeah, the setup actually creates the datasets, but then the data loader themselves, those are returned in the train data loader validation, and if we have one, the test data loader. So this is, yes, I would say this is the most basic examples that we can do while trying to use all the core API of PyTorch Lightning. And yeah, you find these two scripts both in the code folder and in the on GitHub. And Lightning is very good for Slurm-like environments because the oh, sorry, that's a question. Yes, sorry, the question is because I have a typo and I think I must have changed it just before running it for the second time. Also, if you look, it's PyTorch, there is a H swapped with a T in the module import. My bad. I think Ashwin is writing this also in text. Yeah, so Lightning works very well when we have an environment that is based on Slurm, because the number of nodes or devices that we can use can be passed to the trainer object as arguments, and this can be inferred from Slurm environmental variables. So, for example, the number of devices can be inferred by Slurm GPUs per node, and the number of nodes is Slurm number of nodes. So this means that we can get away with changing what we're doing with very little modifications to the code. So one common pattern to do this is to use an argument parser. So we pass to the script some arguments, for example, the number of GPUs, that is number of GPUs per node, the number of nodes that we want to use on Slurm, and what kind of accelerator, and the type of strategy. So for example, here I'm saying distributed data parallel. And I just pass this to the trainer object. So when I call trainer, I can tell it how many devices I want to use, and how many devices per node are present, and how many nodes I want to use. What kind of accelerator and what kind of parallelization strategy. So here, for example, I'm mainly basing this on GDP, since it's what you have seen yesterday already. But when you will see a bit regarding FSDP, you can use this with the same ease of use. It's just a matter of changing a flag. So this makes it very good for this type of use case. I have two examples for later, or for now, actually. One is fine-tuning ResNet, so something to do image classification on the Cifratan dataset. That is a dataset where we have 10 different classes of objects. And this example is more involved, so I think it's good also for you to take and run away with it, so to say, because it includes a bunch of common strategies that we do with Lightning. So, for example, among the type of loggers that we can use, there is a TensorBoard logger. So, like you did yesterday, you can look at the results of your training runs within TensorBoard. And we have among the automatic call or the pre-made callbacks that Lightning provides, there is a learning rate monitor and a model checkpoint that saves a checkpoint after every epoch. And this contains more or less the same things that we have seen, just a bit more involved, because in this example, we have to do some transformation on the data, and this type of transformations we define in the initializer. And then in the setup, we get the data set from disk and transform it according to the transformations that we have just defined. And in here, I have added a couple of to-dos. So in this exercise, you have to define the data loader, like we did in the example above. And here is just what I told you before. So I'm loading ResNet 50 backbone, like skeleton. And yes, and I just construct it in here. And another to do here is to, as we did before, is to unpack the batch, do the forward pass, and compute loss. And we also have something else for the validation step. So this is a bit more involved as an example, because it also include parsing of arguments and launching the trainer that can run on multiple nodes and GPUs. So if you look at the code folder, and you go in the CFAR 10 here, you will find the skeleton that is with these to-dos and a solution. So you basically fill in those lines in the where I left the to-do markers, and the Slurm job also is built in a way that passes all these arguments to the Python script. And here, maybe, yeah, change the solution into skeleton. And then you can test your code, so filled up with the parts that are missing. And this makes it very easy to change on how many resources you're running, because if you want to run on 8 GPUs, you just change the number of nodes into 2. And if you want to run on less GPUs per node, you just change the number of tasks and the number of GPUs. Yes. So what it does here, it just save some of these parameters as environmental variables that you can pass directly to the script. So if you want to change, for example, prioritization strategy, this is the place where you can do it. What the code does also nicely is to save things into a TensorBoard logger. So we can also look at, for example, we can check scalability, like how well it uses the resources that we give to it. So, for example, we can run on 1 GPU, 4 or 8 GPUs over 2 nodes. And once we get all those things into TensorBoard, we can look at how the training goes and how much less time it takes. A bonus exercise that I have put here in the bottom is that Lightning by itself does not save anything regarding wall time. It doesn't have a pre-made callback to check wall time. So you can create a callback yourselves. And I left a hint here, but the main idea is that you check the time at the start of a training epoch and at the end of a training epoch. And then we can look at how much time each epoch takes per using each one of the scalings that I propose, for example, 1 GPU, 4, or 8. So what I would say is that we can wait until 11 for you to do these exercises, and that we can look at the solution together. And I will be present in the Discord channel. So if you have any questions, just reach out. I hope that it was okay. So yes, defining the data loaders here. This pin memory I wrote in the as a hint that they should be set to false. That's actually, I tried a few times. If I don't do that, the data loaders die, and I think it has to do with how much, like if I occupy all the CPUs on one node, which I will do if I ask for 8 per node. Somehow, yes, I don't know if it's a bug or if it's just me trying to be too greedy, but that was interesting. And yeah, what came afterwards was, yes, just return the model as a forward step. So this will just run the whole ResNet backbone, and validation and training loss are just the criterion here, which we have set to be the cross entropy loss, like we did before. Yes, so that was it basically for the exercise. But I hope that the code as it is written here is interesting for you also to reuse in your if you ever try to use Lightning to train your own neural networks. Regarding the bonus, this was about creating a callback. So as I had written in the hint, we create a new callback. In this case, I called it epoch timing, and I just call the hooks at the epoch start and at the epoch end, so we can get the elapsed time to compute one single epoch. And of course, we need the time module to do this. And I had this here in my solution file. And yeah, it is here. One thing that I thought about that could be interesting for you to try is, for example, to look at GPU utilization or like memory occupancy. Since utilization, we need other APIs to do it. And to do that, for example, we can go directly calling torch methods. So we can access the device as the local rank of the trainer. So this will only print on or will only record what's happening on the zero rank, so the lead process, so to say. And we can get, for example, the use memory as directly from the torch CUDA. This is memory allocated from the torch CUDA API, and the same from the total memory. PyTorch.CUDA.get device properties of this GPU. And then we have the total memory. And then what we get as the occupancy is just the use divided by the total. And for example, we can print it here. Now I'm doing it between each epoch. Oh, I have it written here. And I can potentially implement other hooks here, for example, at the beginning of each batch, just to see how because now, of course, if I do at the end of the epoch, the batch will be flushed. But I can implement it in other hooks here. And this will be printed if I run this. Let's see if this runs soon. Yeah. 32305. 630. So now I'm running this on 2 nodes with 4 GPUs per node. And now it's loaded the weights. And now it starts running through all the batches. And I get that at the end of each batch, now I'm making it print from everywhere. I get the GPU occupancy. That in this case is very low because we just flushed the batch. But you can, for example, hook it up at the beginning of each batch loading. And that can be used, for example, to monitor GPU usage, to check if you're using the resource. Now we'll just cancel this. If you're using the resources that you ask for in a reasonable manner. It is also possible to do this over multiple GPUs. Since now I'm using 8 and I'm just printing 1. But to do that, we need to tap into, we need external dependencies. So there is an NVIDIA toolkit called PyNVML that actually allows us to look at each GPU and look at both memory and power, so like the percentage of usage of the cores. And I don't have it here, but I have in this in another example that I'm not going to show because it's pretty much the same, to be honest. This was produced actually by our colleague in Turkey, Ismail, and he implemented a separate callback called GPU utilization. And you can see that he uses this PyNVML. But what it does is at the end of each batch, it gets every device and gets device utilization and memory utilization. So with this, we can get all the information about all the GPUs and log it, for example, to inspect it with TensorBoard. So this could potentially, going back to someone that asked, looking at communication, I think PyNVML has some plumbing also to look at communication time, but I'm not 100% sure. But this, for example, is is an example of callback that you can use to monitor the utilization of several GPUs. And you'll find this in the NIST folder. It's pretty much the same example. So it's still a classification over another data set. But this could be interesting, for example, if you decide to implement something like this. In the example that we just ran, this CFR10, we're using the TensorBoard logger. And we can actually look at the results. So we will log in training and validation loss. And if you add the callback for the epoch timing, you will also get that. So what we can do is, for example, go to the login node. I just logged in into the same folder, still from the login node. And I loaded profile, deep learning, and Chineka AI. You can just start TensorBoard on the login node. And we just pass it the log directory, which is Lightning logs here. And we can pass port 0. This is neat because it just automatically picks some port that is not being used. So we can launch it. And at the very end, it will tell me which port it has chosen. And we can do like we did yesterday. So just open another SSH tunnel, forwarding that port. So now it's here in 39849. So I can do something similar. Is I said 39849. And then I want it on my localhost 39849. And then to make sure that we don't run out into the same issue that we yesterday, since I'm logged in on the login node 2, I will also log on 2 as well. And now if I open TensorBoard here, this port 39849, I will get my nice TensorFlow interface. And these are, well, I can lose the last two since we're the latest run that I've done. Let me make it a bit bigger. So this is what we looked at yesterday. And I can look, for example, here we have the epoch time per second. So how long time each epoch took to run. And I didn't give them different names here because I was using only distributed data parallel. So the naming convention followed just the parallelization strategy. But I, for example, that on one GPU, each batch or each epoch, sorry, took 68 seconds, more or less on average. When I was going on 4 GPUs, I went down to 18. And on 8 GPUs, I went down to 9. So even though the dataset is not that big, it's like 174 megabytes in total, 78. We are observing some good scaling, also because we're not pushing a huge batch size on each GPU actually. So we could probably crank that up before starting to spread. This is obviously overkill for an example that is this small. Close this. But this also, yeah, it's a good way for you to see this as well. So after each run is done, everything that we write in the TensorBoard logger, we just get it like that. So Lightning makes it quite easy because we can choose what to log regardless of the type of logger that we want to use. Now I wrote TensorBoard, but it could have been, for example, just a CSV logger or a TensorBoard, a JSON logger, TensorBoard, obviously. I think also some plumbing for weights and biases, if you are into that. Yes. So yeah, I guess the last thing that I could tell you is that there is this NIST example that again looks pretty much similar, except that you have this different callback that might be interesting for you to look at. And I'm sorry, I think I missed time a bit because I thought that this material will get me a bit further, but I think it was all for me. So thank you for listening, and I will stay online if you have more questions or if you have questions. And yes, I hope that this was interesting for you.
I'm happy to introduce you to our afternoon trainers. And Yeah, today in the afternoon we'll be hearing from NCC Belgium, Geert Jan Bex, and NCC Italy, Riccardo Scheda. Geert will be talking about LLM fine-tuning, and Riccardo about HuggingFace Accelerate and DeepSpeed. Thank you again, everyone, for being here. And Geert, if you're ready, you can start the session. Thank you.
Thank you. So let's try whether I succeed a second time to share my screen. And yes. Okay, so welcome. And this is, of course, directory you're familiar with. This is the GitHub repository for this training event. So you can find all the material for this afternoon's training in the BE directory and the fine-tuning subdirectory. And so the presentation I'm using is also there, so you can easily get your hands on it if you like to check it. Okay, now I try not to get too confused with the windows, because some things are overlapping, and that's a little confusing, but nevertheless. Okay, so let's discuss fine-tuning a little bit. This is a usual thing. That's the Flemish supercomputer LinkedIn page. If you like to follow us, that's always a good idea. There's interesting information there on trainings. Okay, besides that. So basically, this table of contents I obviously forgot to update, so let's skip that. So let's first talk a little bit about a couple of things that normally would be required in order to do the hands-on part. I'll go through it nevertheless, although it shouldn't be necessary on Leonardo because I've prepared a little bit, but it's good to know anyway. So basically, what we are going to use in this case, of course, is the repository which you already know about, so I can safely skip this slide. But what is a bit more interesting, though, is actually the HuggingFace account, which you actually would need in order to do these exercises. So it's always a good idea to have an account on HuggingFace because it's a resource for quite a number of interesting things. So basically, you can sign up. An account is as usual for free. And once you have an account, that would look a little bit like this. Let me go there. And with some luck, I'm automatically signed in, which I seem to be. So basically, there is quite a bit of stuff here. Minimize this thing. Okay, put it somewhere. Sorry, I have to fiddle a little bit with my screen. The important thing, and that is why I'm here and why I'm showing you, is in fact that HuggingFace has an API, access quite a number of resources. So one of the things that's quite interesting is that you can download models, pre-trained models, either with parameters or, well, without parameters, yeah, and they're not pre-trained, of course. But that's, of course, quite useful. Also, data sets and so on. And there is a whole catalog, as you can see, of models, data sets, etc., etc. Now, many of these models are open source and you can download them without any authentication. However, some models are what HuggingFace called gated, so for data sets. So that basically means that you have to agree to an end-user license agreement, which is specified by the owner of that model or that data. And typically, that would be the case, for instance, for anything that Google puts on there. So yes, you can access it, but you have to ask for permission first. So if you have to do that, then you just go to that data set. There is a link which says okay, or that model. There is a link which says okay, please grant access. And sometime later, you receive an email that you can actually, from then on, access that item, whatever it is. If you want to do that programmatically, and that's why I'm actually here, then what you should set up is in fact access tokens. And they should be here somewhere. Try and find them. As you can see, there's quite a lot here. Access tokens, as you can see. And then, of course, I would have to confirm my identity. I'm not going to do that. But basically, you can create as many access tokens as you need. And as usual, it's a good idea to have an access token per computer, which basically means that if something goes wrong security-wise on that computer, that you can easily revoke that token without having to revoke it everywhere, well, without having everywhere to ask for a new token. Okay, so that's just something that's interesting to know and something that I encourage you to do if you are into experimenting with models, with data sets, and so on. Okay, so basically, for instance, an example is gated llama models. So basically, here's a little bit of how you would do that. There's a button here to click, etc. Essentially, that's quite simple. So the model which we are going to use today, which you can use, is Mistral 7 million, and that is a gated model as well. Now, of course, there is a bit of a problem here in the sense that, on the one hand, of course, you could download it from a login node, but that does not seem to work quite well. So what I did was preparing it in such a way that you only need to specify the cache, and that the script then actually will find that module, that model. Note that actually I'm a little bit pushing things here, because essentially what I'm doing is not entirely legal, because I signed the license agreement, you did not. I make the model available, which according to license agreement, I shouldn't do. Okay, so don't tell anyone that I'm breaking the law, but basically that's what I'm doing. Why am I telling you? Well, basically this is train the trainer, and this is a thing trainers might do accidentally and run into trouble with it. So basically that's something that you have to be a little vigilant against, that you are careful with end user license agreement, which again, I'm violating. Yeah, I know. Okay, so let's turn to the matter at hand, which is fine tuning. So question is, why would you want to fine tune a model? Or first, what is fine tuning? Well, basically, you want to solve a problem, and you know of a model that is quite capable of solving similar problems. But they have been trained on general data sets. And you have a more specialized application for which you have a specific, typically small data set, and which you actually would like to get, you would like to specialize a little bit. So I see there is a raised hand, so I'm
yeah, hi. Sorry for a moment because I have a little trouble with hearing what you are saying, probably because of some kind of noise cancellation that is going on in the background with your microphone. And yeah, if you could, for example, in the settings of your of Zoom call, just go with the microphone mode and turn off the option of noise cancellation, because some of the sounds that you say are a bit quieter because of this.
Okay, I'll try to do that, but what I'll also try to do is use a different microphone, because that might also solve the problem.
Okay, I'm first going to try this, because if I have to hunt for the noise cancellation settings within Zoom. So is this better?
This is much better, thank you.
Okay. So it's a problem with this microphone, which actually I paid quite a lot of money for, but basically my built-in microphone in my laptop actually does a better job. Okay, that is Disappointing, but okay. All right, so that solves the problem, I hope. Okay, so again, fine-tuning. So basically, you want to do a specific task, and that task is more specialized than the model you would like to use because it's well suited for that class of problems, is actually adapted to. And then the task of fine-tuning is to sort of specialize that model, to fine-tune that model, to change that model just a little bit, so that it can actually perform better on the particular task you want to do. So for instance, answering questions about a more specific topic than a generally trained LLM. Same with named entity recognition. So basically, of course, many large language models will do acceptable named entity recognition, but if you have a specialized vocabulary, if you have, for instance, in an enterprise, a certain category of named entities, then of course you would also like to specialize on that. So there are quite a number of reasons to try to fine-tune an existing model so that it can deal with more specific things. I'm going to have a look at the chat because I'm guessing there is a question. No, there is not in the Q&A. Okay. So basically, it's domain-specific specialization if you want. Of course, you can do that, and there are many ways to do that. You can simply say, okay, I'm going to use a pre-trained network, and I'm going to retrain it, everything, the whole lot. Okay. On the one hand, good luck, because if it's a large model, that means a lot of computational resources which are required. Do you have those? I don't know, maybe, maybe not. But yeah, you can see that this is a problem. This is also a problem because if you would train a pre-trained model, you would start to modify that, and then of course there are a few risks which you run. One of the risks is you are going to train with your own data set. That's great, but it might be that the knowledge, quote unquote, that model encodes actually evaporates due to your training set that is suddenly way too specialized, and basically you just ruin the existing model. Also, of course, there is a risk for a lack of alignment in the sense that you hope that the the fine-tuned model is going to be aligned with your purposes, but that might not be the case because, of course, you start from an existing model. So this is not really a simple task. It's a task that you should really think about, but it is definitely interesting. So this would be pretty expensive. So why is this so expensive? Well, pretty obviously, the number of parameters is pretty large. And of course, you know that the more parameters you have, the more memory you need. Memory is a precious resource on GPUs. So basically, yeah, that's where the problem comes from. And then, of course, training time. If you have 7 billion parameters, you can guess that training such a model is going to take a significant amount of time. And as I already mentioned, you might encounter a phenomenon which is called catastrophic forgetting. In other words, you get a good training result, but of course, the general knowledge that the model already had might have vanished. So that is a problem. And of course, there is also potentially inference latency. So researchers came up with a smart solution for that, and that's parameter efficient fine-tuning, of PEFT for short. Okay, so basically there are a number of approaches. One of them is using adapters, the other is LoRa or quantified LoRa, or quantized LoRa, sorry. So let's have a quick overview of how that works. So you're not going to retrain the entire model. You are actually going to leave all the weights from the pre-trained model as is. Okay, but then how do you fine tune? Well, basically, you add new layers. So basically, new adapter layers which get inserted into your existing model. So here we have an example. It's, well, for me, a bit unconventional data streams in from the top to the bottom. I usually depict networks the other way around, but okay. That's when you steal illustrations from other sources, then basically, yeah, you don't always get what you want. Okay, so there is multi-head self-attention layer here, and typically in a transformer that is followed by some fully connected layer. Okay, and then basically there is a similar layer here, again with a fully connected layer. And then at the end of the day, we get a norm, etc., etc. So rather than modifying any of these layers by training, what we're actually going to do is to insert new layers. So in red here, we have an adapter layer just after the fully connected layer, and again, an adapter layer after that other fully connected layer. So basically, what you do is you get new parameters in between, and those are used for fine tuning. So basically, those will adapt using the training data you have without, hopefully, forgetting the pre-trained weights or erasing, in a sense, the pre-trained weights. So again, the principle is leave the network weights as is, just insert a couple of new layers and train those. That's basically the idea. Okay, so only those are trained, the others are not. So that is the crucial point here. This has a number of advantages. The first advantage is that it hopefully diminishes the risk of catastrophic forgetting, since you retain all the original weights. And on the other hand, the other advantage is that the number of weights for fine-tuning, so for training, for actual training, is limited and is under your control. As usual, the more weights you make available for training, hopefully the more precise, the more accurate your results will be. On the other hand, longer training time. And of course, everything depends on your data set. Typically, you're fine-tuning with a smaller data set, much smaller than the original. So basically, that means that you should have less parameters to train, because otherwise you are probably in trouble. So of course, as usual, these adapter layers are hyperparameters. Where you place them is a hyperparameter, their size is a hyperparameter, etc., etc. So of course, this is something that you can try to improve upon using hyperparameter optimization. So this is one approach. This is the oldest approach, using adapters. Another approach which is quite interesting is low order rank adaptation, or LoRa. And the idea is similar. So basically now, for me, more conventional data streams from top to bottom. So basically we have our input X here, and we have our pre-trained weights, whatever they are, and we have our output up here. Okay, so the blue part is what we already have. This is our original pre-trained network. And now we're going to do something similar to what we did with adapters, but rather than stacking layers sequentially, we have weights in parallel. So basically, the input vector X not only goes to the pre-trained weights, but also to the part in red here. And that is basically this low order rank adaptation part. So there are two essentially weight matrices, A and B. And basically, as you can see, the rank of that is D times R, and R times H. Let's assume it's D, it doesn't matter. So basically, R is different from D. And that's why this is called low order rank, because typically what you do is you choose R to be less than D, potentially significantly less than D. So basically, then when you have defined this LoRa layer, let's put it that way, then basically you feed X into pre-trained, you feed X into LoRa, and you combine the results in the output. And you start, for instance, from 0 weights for A and B. And essentially what you do is that W, the original W, is now replaced by the original W plus delta W, so the differences in weight, and that's your A times B. Okay, so typically R is less than D, and actually that might remind you of something. So at least me, it reminds of a singular value decomposition, where you actually also have a diagonal matrix, and if you go to order the diagonal elements from high to low, then of course you can set a number of these diagonal elements to 0, and then essentially you keep only the important components of your transformation. And so basically you can see this as a sort of principal component or singular value decomposition, if you like. So it's not the same mathematically, but in a way that is what the training of the network will actually accomplish. It will sort of automatically learn a singular value decomposition. Okay, the crucial point, of course, is that R is smaller than D. So basically, that's why it's called low order rank, and that is very similar to essentially limiting yourself to important ranks in the decomposition. So basically, to the important features which are in this input vector. Okay. So that's essentially the idea. So A times B is a low rank approximation in a way. And of course, just as before, it's only the stuff we add to the network, so basically this A and B matrices, that will be trained. So the pre-trained weights are again untouched, just as before. Okay. Then one of the things that you will very often see is that networks are available in a number of, let's call it formats. So basically they may potentially be quantized. So why quantization? Well, there has been a number of questions a couple of days ago about inference. And of course, one of the things which you may want is that your network fit into, let's say, not data center grade hardware. Not everyone has a H100 or an A100 available in order to do its computations. So basically, you might also want to squeeze that in order to fit onto either consumer hardware or even into mobile or other edge devices. Okay. So what you typically do in that case is that you actually have your model, which is trained in some precision, either in single precision or in half precision. And then you squeeze that even further. You quantize it even further. And there are many techniques to do that. Depending on the time, I might briefly go into that. So for instance, there is normalized float 4. So basically that means that you represent a floating point number using only 4 bits, but in a normalized and scaled way. And of course, that means that you need to retain an offset and a scale. If you would have to retain that for each and every number, of course, then you wouldn't save much. So basically, that is done blockwise. And that is also done blockwise for several reasons. Well, that is done for layer-wise, but not quite. If you would do that for layers, you would have a problem with outliers, because some numbers, some weights would be very large. And then, of course, that goes, if you have this small range, that would go at the cost of the normal range weights. So basically, that's why this is actually done blockwise. So basically, you try to mitigate the quantization errors there. And then, of course, you can do double quantization and so on in order to quantize the constants, etc., etc. So this is pretty aggressive quantization. Okay, but the problem is, of course, that if you have a layer that quantized in this manner, so basically you can't compute with that, because this NF4 format itself is only useful when you know the offset, when you know the scale. Yeah, you have those, but they're not readily available. So basically, what happens in that case is that you take that compressed layer and decompress it, or dequantize it, to use the correct term, as required. So basically, it means you have your quantized model, so view it as a compressed model if you like, and depending on which layer you are executing in the forward pass or in the backward pass, you just dequantize it layer by layer as required. That's essentially what happens, and that is something that the quantized LoRa will do for you. Okay, so I can maybe...
Excuse me, can I ask a question?
Absolutely.
Is this dequantization guaranteed to return actually the original weights, or am I maybe overlooking something in here?
It's not going to be the original weights exactly, but hopefully approximately enough in order not to mess things up completely.
Okay.
But you won't get the exact value anymore, because basically what you are doing, suppose you have something in, pick your favorite data type, say float 16, regardless of whether it's float 16 or brain float, whatever. But basically, suppose you have 16 bits. Okay, now you're going to squeeze that into 4 bits plus 2 numbers. So yeah, you can't retain the original 16 bits, but you hope that if the weights within a block don't differ that much in order of magnitude, that actually the offset and the scale plus the 4 bits per number are enough to retain the information stored in the original float 16 or BF16. That's essentially the idea. So no, you don't get the original back necessarily, but
Right,
hopefully
okay.
something
Thank you.
that's close enough.
Okay, clear.
Yeah. Okay, so maybe I can talk a little bit about quantization anyway. I think we can squeeze it in. Sorry for the feeble pun. So basically, how does that work? In a bit more detail. So this is a picture you're quite familiar with. We have some inputs X we have some weights W, and we produce some output Y, etc., with the transfer function, etc., etc., or the activation function. Okay. So basically, if you look at a concrete example, which you can download from HuggingFace, which is available, Llama 3.2, then the 3.2 means there are 3.2 billion parameters. Okay. However, it takes 4 gigabytes of memory. Okay. You should be immediately a little bit suspicious here, because, okay, even if this is 16-bit floating point, that should be 7 gigabytes. Okay, maybe a little less, but it's certainly more than 4 gigabytes. So something is, and of course that something is indeed, you work in 32-bit.
Sorry, we can't hear you right now.
But at any rate, yeah, I got a message that the connection was unstable. I hope it's back to normal now.
Yeah, it is right now.
Excellent. Yeah, sorry about that. A little flaky from time to time. Apologies for that. So basically, you do your training in some high precision, typically 32-bit or maybe 16-bit, but not lower than that. So that's what you typically do during training. So in order to squeeze you something more reasonable, you
Geert,
either as half
sorry
precision.
for interrupting again. There was some communication problems, network problems, sorry. So now it's working fine, but just you to know that there are some problems.
Okay. Well, I'll switch off my camera. That is likely going to help a bit. Okay. And I don't think you need my face anyway. All right. So basically, we have these weights. Suppose they are 32-bit single precision. In training, and you can represent those by 16-bit floating point or by brain floating point, also 16-bit. Or you can even go, okay, int 8. So integer values, 8 bits. Okay. So the advantage, of course, is that you decrease memory requirements pretty spectacularly. So that's a very good thing. Also, some operations can be executed more efficiently. For instance, tensor cores typically work much more efficiently on quantized data. And they also decrease power consumption. So that's a good thing. Of course, nothing is for free. So a potential disadvantage is that you lose accuracy. You will always lose accuracy. So the question is, how much can you tolerate? On a CPU in order to do floating point computations. You've got 1 sign bit, you've got 8 exponent bits, and you've got 23 mantissa bits. So essentially, the exponent bits are what determine the weight, the range rather, of the numbers you can represent. The mantissa bits are, of course, the precision represented by that you can use in order to represent these numbers. And if you look at 32-bit numbers, then typically that means that you can go as high as 10 to the power 38 and as low as 10 to the power minus 38 with 7 digits of precision. So that's your typical floating point precision. Okay, so this is a bit more in detail about how this encoding works. I'm not going into the details. It's always fun to do this, but let's not do that here. But basically, this is what you get. You get your sign bit, you get your 8 exponent bits, and then you get 23 mantissa bits. Okay. So 16-bit floating point, similar story, slightly different. You've got 1 sign bit, that remains the same. Now you have 5 exponent bits, okay, rather than 8. So essentially that means that the range of floating point numbers you can represent is going to be less than 10 to the 38. And you've only 10 mantissa bits. So basically that means rather than 23 for single precision, you've got 10 for floating point 16. So less range, less precision. Pretty obvious, you only have half the memory space. Of course, if you encode floating point numbers in this way, okay, you can put twice as many in the same amount of memory as you could with the original. That's pretty clear. Okay, so essentially what you get at the end of the day is this representation. Okay, this is cool, but a disadvantage is, of course, that in order to convert from floating point 32 to floating point 16, you need quite a number of operations, which takes time. So if memory serves, Google, I think it was Google, came up with a brain floating point representation. So again, we only use 16 bits. Again, there was a single sign bit, but now the 8 exponent bits. So that's the exact same number as for classic single precision. And you've got 7 mantissa bits. Okay, so essentially that means you've got the same range as single precision floating point numbers, but of course at the cost of quite a bit of precision, because you only have 7 mantissa bits rather than 23. Okay, the advantage, of course, of using BrainFloat 16 is that it's very easy to convert from FP32 to BF16, because the sign bit remains the same, the exponent bits remain the same. The only thing you have to do is to take a little care with the last bit of the mantissa. Apart from that, it's quite easy. So that, of course, makes conversion from BF16 to FP32 or vice versa really, really fast. Okay, another thing, of course, is that very often the order of magnitude differs quite a bit in computations. So essentially, doing those in BrainFloat is actually not that bad, because you can accommodate a wider range. Okay, so you can even go to 8-bit integer representations. And again, here is an example of how you convert that. But basically, the idea is, sorry, a bit too fast. Basically, the idea is that you clip essentially to a certain range. And then, of course, you can actually play the same game for n-bit integers. But what you then store is essentially a scaling factor and an offset or a 0 point. And those, of course, you have to store for dequantification. So, yeah, that, of course, means that there is a problem. If you would have to do that for each and every individual number, then, of course, you're not going to save anything, because if I need to save n bit for the floating point, plus a representation of the scaling factor and of the 0 point, yeah, then of course I'm not going to gain much. So that's why this is typically done at the level of a layer. So you would get a single scaling factor and a single 0 point for that entire layer. No, don't do this at home, it doesn't work. So basically you have outliers in, for instance, the weights or whatever you're trying to quantize. So essentially, you shouldn't just say, okay, I do this for an entire layer. So that's where a blockwise quantization comes in. because then you diminish the risk or you mitigate the effect of outliers. And you, of course, have to store much less scaling factors and 0 points. You only have to store 1 per block. So depending on how many blocks you have, of course, you have larger or less savings. Okay. Yeah, so I already told you this. So basically, typical rule of thumb, use 64 or 128 weights per block, something like that. Seems to work quite well. Okay, similar normalized 4-bit floating point representation. So essentially, you normalize everything between -1 and 1, and you have to keep track of an offset and the scale as usual. And then, of course, you get you bin things into buckets. Given that you have 4 bits, it means you've got 16 buckets, 15 equidistant points, basically to represent your number. And then, of course, it's immediately clear that this is going to be quite lossy if I use compression terms, because indeed, if I only have 4 bits, plus the scale plus the offset, there is no way I can correctly or accurately reconstruct the original number. You just hope it's good enough. Okay. So quantization, there are quite a number of ways to do that. And frankly, it is an active area of research. So lots of algorithms are out there. So I just give you a bit of an overview of what you can do. So something that is fairly easy is post-training quantization. You first train your network and then you quantize. Okay, the advantage is you can always do that. Given any network, quantize it, done. But of course, given that this is done post-training, in the training that has not been taken into account, that you actually want to quantize it. So basically that means that you have a potential risk of significant loss of accuracy. There is also quantization-aware training, and that requires fine-tuning, and it requires training data. So that's an advantage of post-training quantization. You don't need data. Okay, that's not quite true. You still need data if you want to assess the loss of precision, the loss of accuracy, which you suffered due to quantization. But you don't need it for the quantization step itself, only for the assessment of its success or failure. With quantization-aware training, of course, you do need a training set. But the positive side is that you potentially have better accuracy and many other things. Here is an example of quantization-aware training. So basically, you have a difference between the training and the inference, where some layers are just only active when training. Okay. So basically, if you want to quantize your own models or someone else's models, you can easily do that using LlamaCPP. I'm not going into the details here because it's a bit outside the scope. Okay, so let's not go there. The only thing I want to show you is that this was a rather large model. And as you can see, that went really fast, actually. So it doesn't take long to quantize a model, approximately 5 minutes. And this was a 3 billion parameter model. And what you gain is a factor of 4 in size of the model. Okay, so how do you assess accuracy? Well, that's via a measure called perplexity. So basically, it has to do with how surprised are you by the result you get, given the result you expect. That's essentially the idea. So essentially, it's log likelihood for new tokens. That's the idea. Okay. And basically, again, Llama CPP gives you support to actually assess that in a very convenient way. Okay, let's. So this is a bit of a comparison with respect to, on the one hand, the perplexity, then the load time, the prompt evaluation time. As you can see, that also goes down for the quantized model. So indeed, for inference, this is definitely a good idea. On condition, you can live with the increase in perplexity, so the loss of accuracy. And of course, it's much easier to deploy it on more conservative hardware, let's put it that way, because basically your model size goes down by a factor of 4. So this fits easily in a consumer level GPU, while the original model, okay, would work, but yeah, you might struggle a little bit to get it to work. Okay, so the advantages are pretty obvious. You've less memory requirements, faster load of the model, which can also be significant, and then of course faster inference, which is also quite interesting. Okay, that is, I think, more or less what I wanted to tell you. So basically, this is benchmarking. Let's not go there. Okay. Now, this was the introductory part. Let's see how we can do this in practice. So I have 2 things for you. Let me go to Leonardo, where I should be right now. So again, yeah, that's better. Again, we are in the repository. So if you go into the E directory and the fine-tuning subdirectory, the source code, what you'll see there. Okay. Yeah, that's inconvenient. Let me log out and let me go out of Tmux. Okay. And let's increase this a bit. Okay. Let's go back to Leonardo. That's not a success. Yeah, let's try to spell it correctly. That would help. Okay, much better. There was a question in the chat, I think. Let me quickly go there. Yeah, the references. There might be some in the slides. I don't quite recall whether I had some. I think I have actually. Where the heck are my slides? Yeah, that was not smart. Apparently, we closed them. Let me go back. Conclusions, blah, 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 blah. So there are some references here. So the first article I found rather informative. Well, that's actually that's the research article, both for LoRa and QLoRa. Okay, the MCP service, that should not be here because that's not a part of this training. So those are, of course, the articles in which these methods were originally published. I should also have somewhere, but apparently I didn't put it in the slides, an article that talks about a number of fine-tuning methods. I'll try and find it again, and I'll add it to either the slides. No, to the slides would be a good idea. So I'll do that if I can find it again, because I think that was also what I based my training material on. So it should be somewhere. Okay. let me go back here and go to the GitHub repository. Fine-tuning, okay. So well, no, let me go up one level first. So this is the whole fine-tuning stuff. There is a data directory. It's really not much. It's also very empty, which is a bit weird. Why is this empty? Ah, yes, because I'm an idiot. Basically, I moved files rather than copying them, which was, of course, pretty stupid. Okay, let's do this the same way. Let me just get pull. Okay, get restore. Okay. And then the other one. Okay, so yeah, there is also a README file. Okay, now that's back again. So basically, this is what you have in the data directory. The reason why they were not here anymore. Okay, let's take that. The reason why they were not here anymore is that actually the script and also the notebook in the source directory assume that the data is in the same directory where you execute the script. So that was why I accidentally moved it when I was testing things rather than copying it. So that's stupid. Don't do that at home. But yeah, that's why we use Git at the end of the day. So who cares? Okay, so that's the data. The data itself is in JSON-L format, which I'll show you before preparing for that particular data. I had never heard of this particular data format, but it's nothing special. Essentially, it's JSON, but each data item is on a single line. That's what the L is for in JSON-L. It's a line-based format. So each line by itself is a JSON object. So that's essentially the idea. There is a converter script somewhere to actually get normal JSON into JSON-L. It's pretty straightforward. It's just a matter of formatting. Okay, then another interesting directory is the tools directory. Okay, that was elsewhere. Okay, it's a tools directory. So what have we got there? Basically, not that much. Essentially, there are a couple of environment files and also a requirements file. So that allows you to recreate the environments required for this particular training. So essentially, it's not that much. I can show you, for instance, the environment from history. So basically, it's not that much. These are the packages which are required. Again, this is a train the trainer. So one of the lessons learned for me was basically I checked whether everything was present in the module, the Clinical AI model, and everything was there. So I was happy and very confident that that would work. Okay, don't be, because of version hell. Basically, there was something with bits and bytes, which really bit me. Excuse me, the feeble pun. So basically, I had to very quickly recreate an environment using venv because yeah, otherwise it's unfortunately not going to work. So you can easily do that using venv. If you just use the requirements.txt, then you can easily do that. As you can see, I'm a bit of a fan of Mamba Conda, so that's why the environment stuff is here. Okay. Then what else is here? I already told you the PowerPoint presentation is here, and also magically a PDF version of that, I'm assuming. Okay, that's great. That was done for me automatically or by some good spirit somewhere. So basically, this is the directory with the source material, and there are two things. There is a Python script, which you can use with a job script, of course, and then there is also a notebook. So I'm going to walk you through the code using the notebook. I'm just going to open that locally, just to simplify things, conserve bandwidth, and retain my sanity, just to be sure. So let me go to my original for this. Okay. So you can open the notebook on Leonardo if you want, just to keep things simple. I'm going to do it locally. I'm not going to execute it anyway because it takes quite a while. So I'm just going to walk you through the code. Okay, so this is the notebook. All right. Basically, one of the things you can specify is the CUDA version. And basically, you see the BNB prefix here. So that's actually bits and bytes, a configuration framework, which we will use further on as well. Okay, these are some helper functions. So basically, this is a model that expects a prompt, and the prompt is in the format question, and then answer. So basically, this is just a function that, given an example, is going to format it in this way so that we get a prompt for the LLM. Okay. So one of the things which we're using is datasets. So that's a package from HuggingFace, which is quite convenient. It can store all kind of data. You can use it for textual data, for image data, and so on. It is quite convenient. Okay, so then we can load the dataset. We specify the format, and we specify the file in this case. And in this case, this is the train split. Okay. And then I also have the test file. So again, this is train. Don't worry, this doesn't matter because those are different files. You see, I've got a set with training questions and I've got a set with test questions. So the split is actually not really being used. Okay. So basically, normally the number of examples should be here somewhere, but I don't see them here. Okay. Then I'm going to use a number of things from HuggingFace. So that means I need to log in. And there are several ways to do that. So in a notebook, you can use, and maybe I can execute this anyway, just to show you. We just execute this. Okay. So basically, this is sort of a login. And why does that fail? Okay. something I didn't install in my environment, so I need IPy widgets. Okay. Okay. I recreated the environment and apparently I forgot that one. Then tested the script and not the notebook. Okay, it happens. Come on, come on, come on. All right, so that's it. Let's remove that. That's not very interesting. And let's re-execute this guy here. Okay, so now something should happen. Okay, it doesn't. Yeah, okay. So it got a little bit smarter. I've got an environment variable set that actually contains my token. And given that that is set, and this version of the Hugging Face Hub is a bit more intelligent than the one before, I'm actually not prompted for my token. So normally you would get a dialog in which you have to paste your Hugging Face token. Remember, that was the thing I said it's useful to create. Okay. So let me maybe go quickly to the script itself. Pum, pum. I want to open this guy here. Because it's done in a slightly different way. And actually here I have to be a bit careful because this guy, and that's important, in the script you have this is already okay. In this script it's not okay. So one of the things that you want is to actually have this statement here, and I'll explain in a second why. Okay, so basically, as I mentioned, what you need is a token. And of course, a token is personal. A token essentially represents credentials. So that's something that you should never put in a version control repository. So you have several ways of dealing with that. The simplest way is to say, okay, I'm hard coding this. That's a bad idea because then you're leaking a secret. That's something you should never do. Okay, another way is that you simply in the shell do something like, let me go somewhere, something like export HF token, because that's the name of the variable, and then blah, 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 your token. Okay, that's great. And yeah, you're going to be unhappy because how are you going to do that when you have a job script? Okay, then of course you can put the token in your job script, but then again we're in the same, we have the same problem because that goes under version control and that's something you don't want in order to leak secrets. So basically what you do is you actually write a file which I've got here. So basically, I'll show you the content because it should be normally a sanitized version. What did I do? That's yeah, and then oh, sorry, no, this is not all word. Okay. sorry, I need to find it. Where did I put this thing? I think it is here. No, I don't have one. Okay, so basically the file simply looks like this. We can simply create one. So basically, okay. Yeah, the problem is I can't show you because my key is in there, and this is recorded, and then I have to retract my key, etc., etc. So I would like to show you an example which doesn't contain my key. That would be more convenient, but let me just create one. So basically, going to remove this one, and I'm just going to create a new one. So basically what you do is you set HF token, the HuggingFace token, to whatever. Okay. You create another one, HF home, and this you can also set to something, and this is important here if you want to execute this, because the problem is that if you want to download that model, I didn't succeed to do that on Leonardo for some reason, on the login node even. So that's a little bit weird. My process got killed. I didn't bother to figure out what the problem was, but basically this is not really going to work. So what you can do instead, because I already did that, the model is in fact here in fast models cache. So basically all the stuff which should come from HuggingFace is in fact here. So that means that if you set and I'll put that in the chat as well. This. Okay. Then it's going to use this cache, and that actually contains the downloaded model and some other stuff, which otherwise would come from Hugging Space. Let me put that in the chat somewhere. Should likely go here, I think. No, I'll put it in the Q&A. It will be the simplest thing. Okay, so that would be important. Okay, now you have this small file. Okay, and you also have this .env here, and basically you load .env. So essentially that means that the variables, the environment variables defined in that .env file will be part of your environment. If they're part of your environment, the modules which we load here, Hugging Face modules, can actually load those. So that happens in the script, but that also happens in the notebook. Okay, why is it important? I mentioned that the script which I was showing you wasn't correct. So this is the correct version. The reason is that these environment variables must be defined at the moment you import these modules. Otherwise, the default values are taken. And then, of course, for the Hugging Face home directory will be your .cache directory in your home directory. So that's not what you want, because then you're forced to download a whole lot and to redo all these things. So in the repository, this is already correct. You don't have to worry about it. Okay, so then we load some stuff. Let's not go there for now. We logged in. Let me switch back to the notebook. Okay, we log into Hugging Space, etc., etc. Then configuring and downloading the model. So basically, we import transformers. We have auto tokenize, auto model, causal LLM, etc. Bits and bytes configuration. Okay, so we set up the base model, and as I said, that will be Mistral 7 billion. Okay, and then we configure a number of things. So this bits and bytes config allows you to set these things. As you can see, it will load in 4-bit. So this is a quantized model, and it will also use double quantization. Let's not go into the details, but that basically means that you quantize the quantization parameters. So basically the scaling and the offset. And then the quantization type is NF4. Remember this normalized float, 4-bit. And what you want to compute with is actually brain float 16. So that means that if I need a layer which is compressed to NF4, it's going to be decompressed, dequantized into brain float 16, and that is going to be used for the computations. Okay, so basically, then we create the model based on the base model, the quantization configuration, and the device, which is auto. This is nice. This is going to do the right thing. Meaning, if this runs on a computer without a GPU, it's running on the CPU. If there is a GPU detected, it is going to use the CPU, the GPU. Okay. So basically, this takes quite a bit of time. If it needs to be downloaded, that is what is actually in that cache directory, which I put on Leonardo this morning. Okay. Then, of course, we need tokenization in the sense that we have new training data. That data is not tokenized. So what we need is the tokenizer that is part of the pre-trained model. And that's what we're getting here. So basically, from the base model, we get that pre-trained tokenizer. We set a few things here, padding and adding an end file token and so on. So a number of small details. Okay. And then this tokenizer is in fact also downloaded from HuggingFace. Okay. Then this is to generate and tokenize the prompt. So basically it uses the tokenizer and the format prompt function, which we already used. Okay, so we want at most 200 tokens, whatever. So basically not so very interesting. So then we're going to tokenize the input data, so the training data and the test data. Okay. This is just a quick check that indeed all my examples are exactly 200 tokens long. So basically that is quite straightforward. Okay, then of course, since we are going to fine tune, we need a little bit of a performance benchmark. In this case, this is very straightforward in the sense that this is not let's say, a rigorous way of doing this. What you should do, of course, is to run this with a measure of perplexity for the training data and the test data and see where you end up when you have done the fine-tuning. But okay, this is just to show you that actually this he can answer the question, although not very well. Okay, so basically, again, we have an evaluation tokenizer. We have the model input, which comes from the tokenizer. We have the evaluation prompt, and then we evaluate the model. So we put it in evaluation mode, and no gradients, of course. We just evaluate that simple token, that simple question. And then normally you get an answer. So basically, as you can see, this is not very informative because I would like to get the answer to this question here. How do I concatenate data frames along rows in pandas? And then I get this answer, which is nice, but yeah, it doesn't work particularly well. So basically, we hope that after fine-tuning, that will, of course, be a bit better. Okay, so let's turn our attention to fine-tuning itself. How do we do this in practice? Well, basically, we need to know how the model is structured. What are the layers which we have here? And this is very simple. We can just print the model, and then you see that we get all the layers. So basically, what you see is there is a self-attention layer here. As you can see, there is a multi-layer perceptron layer here, etc., etc. Okay. So basically, as you can see, this is the total model structure. All right. So how are we going to fine-tune? Okay. This we can do using a module called PEFT, so for parameter efficient fine-tuning. So this is essentially going to be a to-do LoRa. Okay, we need to configure this. Okay, so our configuration says that R, remember that's the dimension of our one of the dimensions of our A and B, so the small one. We set that to 32 in this case. And then we set a number of parameters for this algorithm. And then crucially, what we set are the target modules. So basically, those are the layers in our network, which we actually want to use LoRa on. And as you can see, we just use the name of the layers, which also occur here. So the projection matrix, the query matrix, the key matrix, the value matrix, and so on. So basically, these guys here. And the gate projection and so on, a projection, down projection. So all these layers will in fact be fine-tuned. Okay. We don't set bias. We have a certain dropout just to ensure that we don't overfit too much. And we set a certain task type. So basically, this is a causal model. So yeah. Okay, a causal language model. Then we have the PEF model. Okay, so basically, this is our training model and our configuration. Okay, then we can write a small function to print the trainable parameters. And if we do that, you see that we have in total 2.2% of trainable parameters. So of course, all our original parameters, all the original weights are fixed and remain fixed. So what we have added is approximately 2% new parameters. This is reasonable. It's maybe a bit large. So typically, rule of thumb is pick something between 1 and 2% for the number of LoRa parameters. That's a good rule of thumb. So a bit on the high side, but okay, it's still quite acceptable. Now, if you print the model, now this is the PEFT model, so that's the one that's already been augmented with the LoRa weights, you see that indeed here now there is quite a bit more. See, there's a LoRa linear, etc. You see that the structure of the model has been changed automatically for you. And basically you see that here is a LoRa A and a LoRa B. And you will see that reoccur a couple of times. So those are the new parameters which will be determined by training. Okay, so we do have a significantly more complicated model now, but with not that much more parameters as the original. Okay, And then this is something that will be discussed later this afternoon. So that's again HuggingFace, the Accelerate package, which basically means that I can very easily run this on 1 GPU, on 2 GPUs, whatever. And the vision of work is going to be done for me. Okay. So basically, I'm here on a CUDA device. So if I have more than one device, more than one GPU, then basically this is set to parallelizable. So then indeed this can be parallelized, and it is going to be model parallelization. So basically it's going to be layer parallelized. Frankly, that does not make any sense here, because basically this is going to be very counterproductive. I would suggest you try it. What you will see is that the training time with one GPU or with two GPUs is essentially the same. So this is not going to help in this case. And that is in fact one of the design goals of LoRa. This is actually an algorithm or an approach that was specifically designed in order to reduce the memory requirements or the computational requirements, and or I should say of this particular method. So that is of course a very good thing. Of course, if you have a really, really large model, then again, it might not fit into a single GPU, or you might need more compute power than can be delivered by a GPU. If so, then of course, parallelization over multiple GPUs does make sense. For this example, you can try it. It's not going to give you anything, but okay. It's also very easy to do. You only have to run it with in a batch job that has access to multiple GPUs. Okay. Then basically, again, we set a number of parameters. So this is just bookkeeping all of this. This is going to create a directory, or rather to define a directory and so on. You set a learning rate, and then you define a trainer. And again, we have a million parameters here. So basically, we have the accelerated model as a model. We have our training data set. We have our evaluation data set. Those are the tokenized sets we created before. And then we have some training arguments. You see an output directory, a warm-up step, etc. Per device training batch size. That can probably go up a bit, and so on. You see quite a number of parameters which you can play with. Okay, and then at the end of the day, you can configure, use the cache, that's another optimization, and finally train the network. Okay, so this has actually run on my own laptop, which has a RTX 3000 something, 80 I think, or 60, I don't quite remember. But basically it runs rather comfortable on my laptop. And as you can see, indeed, the training loss and the validation loss go down nicely. And here I ran out of patience essentially. So basically I stopped the training. Yeah, so this is something that you can try for yourself. On Leonardo, I would suggest you use the script version of this rather than the fine-tuning version, than the notebook version, just so that you can submit it as a batch job and look at it, look at the results later on. So with this settings, each 50 epochs, if memory serves, I hope it's 50, maybe it's here somewhere, one of the parameters. Every 25, there is a logging step. The save step is here, 25. So you might want to increase this a bit, because otherwise every 25 steps you will have a checkpoint. Okay, that consumes quite a bit of disk space, so you might want to avoid that. Okay, that is about what I wanted to tell you. So if you like, feel free to try this out. I don't have a particular job script for this, but it's very straightforward. However, I would suggest you create an environment for it because, yeah, due to some versioning thing, bits and bytes refuse to work on Leonardo for me with the Clinica AI module. It ought to work on the with the environment I gave you the specs for. Okay, are there any questions?
So, hi, nice to meet you. I'm Riccardo. I'm an HPC data engineer at Cineca, and now we will talk about fine-tuning with Accelerate and fully shared data parallel. So, as you know, in the AI field, there are two main problems with pre-training and fine-tuning models. The first is that training a model could take a very large amount of time, and so you have to wait many times to train a final model. And on the other side, there is often the problem that if a model is quite large, it can fit in a single GPU memory, and so we need more resources. And to do that, to solve these two problems, we have different techniques that we will see. In general, this type of parallelisms can be divided in three. The one that you saw in the previous lecture was data parallelism and model parallelism. And today we will see a type which is in the middle, which is called model sharding. Model sharding is divided in two main techniques, which are fully sharded data parallel and zero stage, which is developed by Microsoft, while fully sharded data parallel is developed by PyTorch. If you want to look to all of the techniques of parallelization, you can see this page in the HuggingFace site. Okay, so let's dive into the model sharding technique. On Leonardo, we have the GPUs, which are Ampere 100, with in a custom setting in which we have 64 gigabytes of memory. And so when we want to train a model, let's say, for example, a 7 billion parameter model on Leonardo in full precision, so in FP32 precision, we have some problems because we have to put in memory all of the parameters, the activation, the gradients, and also the optimizer. And in total, we will have 140 gigabytes of memory. And also in half precision with FP16, we end up with 70 gigabytes. So training a 7 billion model in Leonardo, we need to parallelize it. So in principle, sharding, it means that we split a model in different parts called shards, in which these shards can hold the parameters, the optimizer states, and the gradients across different GPUs. And this indeed enables large models training. And there we will see that we have different types and methods to divide optimizer states and gradients. So in principle, the main difference between distributed data parallel training and model sharding is the fact that in distributed data parallel, the model is replicated across the different GPUs, while in model sharding, we have one single model that is split in the different GPUs. So the replica of the model is one. But also we will have that the data are divided across the GPUs. As I said, we have two main techniques for model sharding. The first one is called zero redundancy optimizer, made by the tool DeepSpeed, which can be also divided in three different stages, in which the main difference is that is on what you split across the GPUs. And also we have from PyTorch fully sharded data parallelism, and we will see in details in the next slides. So in principle, the pros of these techniques is the memory footprint, as we said, since training a large language model in one single GPU is not feasible. But as cons, we have that the cost of the communication volume is increased because obviously if we divide the model in different shards across different GPUs, if you want to synchronize the parameters, the optimizer state, and the gradients across the different GPUs, we have a lot of communication during the training. And so this is the main cons, if you want. So let's talk about zero. If we take only stage one of DeepSpeed zero, what we divide is only the optimizer states, in the sense that the parameters and the gradients remain replicated equally on all of the GPUs that we have, but the only thing that we split are the optimizer states. In the stage two, instead, we split also the gradients. So what remains replicated are the parameters between the different GPUs, but the optimizers states and the gradients are splitted across. And again, in the third stage, we have that we split everything. So we split the parameters, the gradients, and the optimizer states. Obviously, there are these three different stages because, let's say, if you have enough amount of resources in a single GPU, we can use stage one, in which we have replicated the gradients and the parameters, but we have to split the optimizer states. Then, if we have not so much resources, we have to split both the gradients and the optimizer state using the stage two. But also, then, if we again have not so much resources, we are, let's say, obliged to use stage three and split also the parameters of the model. So it depends always in the situation that you are. And the stage three, so the situation in which you split the model parameters, the gradients, and the optimizer state, is the same as PyTorch fully sharded data parallel. It's the same technique, but it is optimized by PyTorch. So let's see what is composed of fully sharded data parallel. Before diving into the technique, let's make a recap of the principal communications between the different GPUs. The first type of communication that can arise between the GPUs is the so-called all reduce, in which, let's say that in each of the GPU we have a different content. So in the first GPU we have let's say A, B in the second, C in the third, and D in the fourth GPU. So in each GPU, we have different values of some parameters. If we perform the all reduce communication function, we will end up with all the four GPUs with all the same results. So the sum of all the content of all the GPUs. Then we have the function reduce scatter, in which each GPU receives the results of the sum of only one part of the content of each GPU. So, for example, in the first GPU, we will have only the sum of the first part of the content of each GPU. This is called reduce scatter. And then we have also the all gather function, in which each rank receives the contribution of the other ranks, but not the final results, in the sense that each GPU will end up with the same content, but not summed. So we will have in the first GPU, we will have all of the parts of the GPUs, but not summed up. Okay, so we have done this little recap, and we will see in a fully shared data parallel how it works. So in fully shared data parallel, we do thing which is similar to other type of techniques, which are model parallelism and tensor parallelism, but not equal, in the sense that in model parallelism and in tensor parallelism, you divide the model in horizontally or vertically. Here, instead, you do, let's say, a mix, in which if you have a model, you will take a model shard, like in the GPU 0, which is a part, literally a part of the neural network, which is put in the GPU 0, and you do that for all of the GPUs. But it's quite different from model parallelism and in tensor parallelism, in which the blocks are fixed and in which are, let's say, not fragmented. Here, in this FSADP instead, we have that, for example, the first layer is divided in two, but also the other layer of the models. And how it works, the training in this setting. So firstly, we will have the forward pass, in which the data will be used as input for the first layer, but you have to consider that the first layer, in this sense, is only in the first two GPUs, and in the other GPUs there is no the first layer. So in order to use all of the resources before making the forward pass, we have to pass these parameters to the other GPUs and then perform the forward pass, and then again make the function all gather for the second layer of the neural network. So in order to have the second layer also in the other GPUs. We do this for all of the layers of the model, and then we have to make the backward pass, which is done in a similar way. But in this case, we will have two different functions, which are the all gather and the reduce scatter. I know that this might be quite confusing, but I will show you a video that I made in which I hope that you can see. the video. Here you can see that the model is divided in 4 different parts, and you can see that the first layer is sent to the other GPUs, and the forward is performed on all of the GPUs. Then the second layer is split and is sent it to the other GPUs. So for the third layer and for the fourth. After that, we have to make the backward pass, in which we can see that at the end, when the last layer is updated, only the GPU 1 and GPU 3 as the last layer. So at the end, we will end up with the model that is again sharded across the GPUs, but only, for example, the first layer is only physically in the GPU 0 and GPU 2, but with updated parameters and optimizer states. I hope that this video is more clear than my previous explanation. Okay. So when we do profiling of the training of different parallelization techniques, we can also see in these profiles that distributed data parallel and fully shared data parallel, we can see that the behavior is different, in which during the backward pass, the main function of the distributed data parallel technique is the null reduce between the GPUs. And instead, in the fully shared data parallel technique, in the forward pass, we will have a null gather function, and in the backward pass, this is not so clear in the image, but in the backward pass, we will have a null gather plus a reduce scatter function. So you can imagine that rather that with respect with DDP, fully shared data parallel has a lot of more communication between the GPUs. Okay, now we have another technique which is called hybrid shared data parallelism, in which we have like similar to FSDP, but here we have different replicas across the nodes, in which, for example, in the first node, we will have the model that is sharded across of the GPUs of the single node. And this is replicated for all of the nodes, and it is kind of a mix between DDP and FSDP, in which in each of the nodes, the model is replicated. And as a pro, we have a reduced communication volume because the model is not sharded across all of the GPUs of all the nodes, but is sharded only in one node and replicated across the nodes. But of course, you will need more GPU memory with respect to FSDP. Okay, so let's put in practice what we saw using HuggingFace Accelerate. In order to do training in a multi-GPU or a multi-node setting, in particular a fine-tuning in a multi-node setting, we can use Accelerate developed by HuggingFace. Indeed, Accelerate allows distributed training across multiple nodes, and is very convenient because the configuration is very easy. And we will see now how to make a configuration of Accelerate. And with Accelerate, we can use also different type of parallelism. So if you want, we can try to configure Accelerate using the config file and creating it. So maybe I can, if you want to do so, I can give you the command here. I will put the command in the chat, or maybe you can only if it works. Okay. If we have Accelerate, if you're trying it and doesn't work, let's try. Mm. Okay. Mm. I will read. Okay, this model should have Accelerate. Okay, with module load Cinec AI, it works. So sorry, I show you again. You have to do if you want to try. Load. You have to do it like this, and then Accelerate. Okay, we want to do it in a multi-GPU setting, so we put multi-GPU. How many different machines we will use? We can use, let's say, 2 machines with two, in the sense that we use 2 nodes. What is the rank of this machine? This is not a problem. We can put 0, and also the IP address is not a problem. So we put enter. Also, the port is by default, and we can. Oh, maybe we have. I put it in the job script. I think that we can put 6,000. Are all the machines on the same local network? Yes. In Leonardo, we have the machines that are all in the same network. Should distributed operation be checked while running errors? We can say no. Do you wish to optimize your script with Torch Dynamo? In this course, no. Do you want to use DeepSpeed? No, because I want to use FSDP, but you can also try DeepSpeed. Do you want to use fully shared data parallel? Yes. Which type of, what should be your sharding strategies? In this example, we will try full shard, but as you can see, we can, as I showed you before, you can also use different type of sharding, in which, for example, we have shard gradients and optimizer states, no shard, hybrid shard, but we will go with full shard. Do you want to offload parameters to GPU? No, I think this is a problem of memory, in which if you want to save more memory, you have to say yes. It depends on the different cases, but here I think no, it is enough. We will use the Llama model, a MetaLlama, which is a transformers based. So we will put transformer based. And do you want to use no split model to wrap? Only applicable for transformer. We can say no by default. Specify the comma separated list of transformer layers name. So I don't remember the transformer layer because it's not listed here, but we can go also by default entering without saying nothing. And also here, what should be your FSDB backward prefetch policy? We will put backward prefetch. And also we can choose the state dict, how it will be sharded. Full state dict or sharded state dict. We will put this by default. And also, do you want to enable FSDP forward prefetch policy? We can say no. If you want all the details of these parameters, of course, you can go in the Accelerate documentation, which is explained all in details. Do you want to enable FSDP original params? Yes. And typically, you can do the arguments that are set by default. So, do you want to enable CPU RAM efficient model loading? Yes. How many GPUs should be used for distributed training? So in the beginning of the questions, we put multi-GPU and we put two different machines. So since in Leonardo we have 4 GPUs for node, we will put 8 GPUs. Also, do you wish to use FP16 or BF16 mixed precision? We can also put no in this example, but you can customize all of these parameters. As you can see, if you do this by default, so as I did, like accelerate config, it will save the file in the cache of HuggingFace. But you can also explicit the path of your config file, like this. And it will save it in my own path, in my folder. And okay. Okay, this was an example on how you do the first config file with using Accelerate. As you see in the GitHub repository, there is predefined configuration with FSDP that I did, and you can see also the parameters that I used, in which I used full shard and transformer based wrap with 2 machines, and the number of processes, which is 8, which is the number of GPUs. And then in the exercise, in the next exercise, we will use it. Okay. Okay, as I said, there and as you saw in the configuration during the making of the configuration, Accelerate asks you if you want to use the CPU, GPU, or other type of accelerators, and also the number of processes, number of machines, and so on. It's very customizable. And also we set FSTP, but also you can have different different strategies like DeepSpeed and NVIDIA Megatron LM. How do you launch an experiment with Accelerate? Simply, you will use Accelerate launch, and with the config file that you made, and also with your Python scripts. Since we are in Leonardo and we use Slurm, we need to put the master address and the master port, which is given by our job script, and also the machine rank. I will show you in a moment. Okay. In the here in the table, I've done two launches, two different experiments, in which I can see that with only one GPU and one node, my model takes like 3,000 seconds, and using instead 2 GPUs, it takes like half of the time. So as an exercise, I want you to do the experiment for 4 GPUs and then also for 8 GPUs in order to see how the training speed up. To do this, make sure that you have pulled the repository, because I have updated it just before the previous lessons. So make sure that, sorry, let's try to. Okay. So make a git pull of the repository. Maybe I have some errors because of. Okay. Okay, I did some modification, but this is not a problem. Then you can go to my folder, which is Accelerate FSTP. So, for example, CASTIEL, IT, and Accelerate. And here you can find the config file, the job file, and the Python script. Now, we want to run the job for 4 GPUs and 8 GPUs, adjusting also the number of the nodes. keep in mind that you need to change also the configuration file, because before we made a configuration file which has 2 machines and 8 processes. But in the case that I want to use 4 GPUs, I have to change both the job script and the configuration file. So let's change, for example, for 4 GPUs, no, 1 machine and 4 GPUs in the configuration file, but also we have to change the job script. So in the repository, I've left you empty this space, which is the number of nodes. In this case, the number of nodes is 1, and the number of GPUs in Leonardo is, for each node, is 4. So we put 4. I think that we can cancel this. And then we should be fine. After that, we can launch the job. With the reservation, the job should be okay. Maybe I got an error. Sorry. That's good. I'll check. We can try 1 and 4, and also I want 1 node and 4 GPUs. Let's see. Batch job, and you need to see the status of the job completing. I have an error. Oh, maybe because if you loaded a module, maybe it can be the problem. So be sure to have done module purge before I've launched the job. Okay, now it should work. To see online the update of the job, you can do tail -f of this. And you can see the job that is running. Also, keep in mind that if you have a job that is running, you can also, without waiting, you can also modify the job for the other experiment. That the GPUs are 4 for each node, so I have to modify also config file, and to do the experiment with 2 nodes and 8 GPUs, we can launch the same job even if the first job is running. So now we have both of the job which are running, and as I showed you, we can see inline the update. Okay, let's see. We have something. No. Okay. I think this is the main problem. Oh, okay. The other one is going. If you want, okay, this is quite slow, but if you want to, I left also, if you want to maybe to reproduce the exercise and to make your own environment, I left the requirements file, and I'll show you how to create an env on Leonardo. You have to, before you have to load the Python module with module load Python, and then create a virtual environment. This Python -m venv and the name example m. After that, you will see that you have a folder with the environment inside, and to activate it, you have to activate env. And then you can install the requirements. It's finished. This type. So it finished. So let's see the output. Okay, so sorry. So we see that in this training it took 530 seconds. And in this case, we had so we had like that in this case. Now I think this is stopped. I don't know why. That is strange. Okay, no problem. I think that is a problem of environment, but let's keep this job in which we saw that it took 537. Okay, so I think that this should be here. So here you can see that the training, the fine tuning with 4 GPUs is much less than with 1 GPUs and 2 GPUs. If you want to finish the exercise and to make sure that training time and the speed up follows the ideal, which is 4 and 8. I'm not sure if skip. Maybe I did the wrong. Okay, and 530 was the job with 2 nodes and 4G and 8 GPUs. So if you want to check the job with 1 node and 4 GPUs, it should be 4 times. And this is the speed up in particular is like 6.9. Yes. So ideally it should be 8, the speed up, but we are in the real world, so we get worse results, but still pretty impressive. Okay, from my side that's all. As take-home messages, I would like to say that you can see many different tools for fine-tuning and different strategies of parallelization. And there is no a clear answer on which I have to use, but I think that the best answer is the tool that you want to use it the best in which you are more comfortable and it is more clear for you, and obviously in which in the situation which is more suitable for you. But actually, I don't think that there is a best answer. I hope that it was everything clear, and thank you very much for being here too.